Okay, so this last video in the series for these 2 weeks of classes is about two examples of continuous operation over this space of continuous functions from 0, 1 to R. What are the two operations we're going to discuss? They're over here. One of them is convolution. I take two functions and I take this funny integral. Well, f star g of t is the integral from 0 to t of f of s and g t minus s. Does this make sense? Well, does this give us a new function? It does, right? Because for ht, I have a well-specified value. Well, you have to check that I'm only computing f in points s that are between 0 and 1. That's true because t is between 0 and 1. And the same for g, because if t is between 0 and 1, and s is between 0 and t, then this number in here is also between 0 and 1. And I have a product of continuous functions. It's continuous. I can integrate it just doing the ordinary Riemann integral. So this is well defined. For each pair f and g, I get a new function. This is one mapping you're going to consider. And the other one is this transformation t that I'm going to explain later. Let me say for now that it's related to solving ordinary differential equations. Somehow existence and uniqueness theorems for ODEs are essentially theorems about this operation here. Okay, so here I have a calculation that I have written down for you. So let me start by saying that we don't know yet, and I think it's not entirely obvious, that when I take f and g continuous and I do the convolution, it's not completely clear that this is continuous as well, right? Or is it? I don't think it is. Because, well, I mean, you have to check carefully that somehow when I vary t, this expression varies continuously. That's not completely obvious. But let's take that as a fact for now. Let's assume that's true. In that case, I think it should be clear that convolution is a bilinear function or a two-linear function. Why? If f is a sum of f1 and f2, then I get f1 plus f2 times g here. The sum splits into two. The integral splits with the sum. So the sum, if f is f1 plus f2, I get a sum on the other side. Similarly, if I multiply by a scalar, I get the scalar popping out of the integral. And the same is true for g, right? So it's linear in both f and g, and that's the definition of two-linear or bilinear, like I sometimes call it. So if it's true that the convolution is a continuous function, what I have here is a bilinear map from c times c to c. And to prove it's continuous, all I have to do is to show it's bounded. Therefore, what is that? I have to compute the norm of conv fg, divide by the product of the norms of f and g, and show that the ratio between these things is upper bounded by something finite. That's what bounded means, and boundedness we know is equivalent to continuity for two-linear or bilinear maps. Okay, so let's do that, right? So we're going to compute the infinity norm, so we need a bound over this, right? So this is a value of a convolution at t. We need a bound over this that's uniform in t, so that we get a bound on the sup of this. So convolution is this, which is this. Then I use this fact from a previous class, which is that the absolute value of an integral is always at most the length of the interval times the sup of what's inside. But the sup, I'm just going to say, well, the maximum of f times g is at most the maximum of f times the maximum of g. Even if you take absolute values here, it doesn't change. Right, so I should have here the maximum of s times g t minus s, but I say that that maximum is at most the product of the maxima, the individual maxima. Okay, with that, I'm almost done. I still have t here. I'm going to get rid of it, so I just say, well, t is between, sorry, this shouldn't be a, this should be 0. 0, or then you call it, I guess you call it t minus 0 to be t. And yeah, so this is, well, t is between 0 and 1, so this is at most 1. So I get just the product of the norms. And here I have to fix things too. So there's no b minus a. I mean, the reason why I have b minus a here is that, you know, we can consider continuous functions from a, b to r, but that doesn't really matter right now. So, okay, so once you get here, you have the norm of the convolution is always less than or equal to the product of the norms, and therefore you have this inequality here. And from this, you can, what is this, right? By definition, the supremum is the norm of this bilinear map from C times C to C. This says it's less than or equal to 1, but it's also equal to 1 because it can take f and g to be constant functions equal to 1, and then you have equality in all my calculations. So we know how to compute this norm. If I somehow had convolutions from a, b to r, I get here the length of the interval ab, which is b minus a. You have to be a little more careful with definition of convolution, but that's no big deal. It can be done. However, what we have not done, and is not so trivial as I said before, is to show that the convolution of two continuous functions is continuous. And as I mentioned in the previous video, there's a lot more to this. Somehow convolution is a smoothing operator. Suppose I put in a function f that's maybe not even continuous. It has a finite number of discontinuities, but g is a very smooth function. It turns out that this convolution of f and g is also very smooth. So it's somehow as smooth as the most smooth of the two of f and g. So it's a nice operation. It's useful in analysis, also related to many things in signal processing. Somehow linear filters are filters that correspond to convolutions. But we still don't know that the convolution of f and g is continuous whenever f and g are continuous. So we're going to prove that now. And as usual, we're going to need a few things from analysis over R, which I'm going to remind you of. Right, so first perhaps you should try to think for yourself how you'd prove that such an operation is continuous. That f star g is continuous. I mean, it's not entirely obvious, at least as far as I'm concerned. And now you're going to hear the noise of water, maybe, because I need some water to properly erase the blackboard. Okay, so I think it's not obvious. Hopefully you agree with me, otherwise that means I'm stupid, but okay. But okay, let's see. How do we prove this continuity? So we're going to use a fact that's very important in analysis, which is that a continuous function over a compact interval is uniformly compact. What do I mean by that? Fact. For all epsilon greater than 0, there exists a delta greater than 0, such that for all points t and t prime in the unit interval, if the distance between t minus t prime is less than delta, that means that the distance between g of t and g of t prime is less than or equal to epsilon. So this is uniform continuity, is a fact from analysis over the real line. It's actually a fact that's true about continuous functions defined over any compact matrix space. But we don't know what compact is yet, or maybe some of you do, but we haven't really discussed that in class. That will come later. But for now, we just need this version where the domain of the functions is 0, 1. And notice that I just stated this to G. Okay, just as a reminder, why is this called uniform continuity? Well, look, the usual statement of continuity, there are many versions, right? We stated it in this version of convergence sequences. Another one that we're going to see pretty soon is that if I give you a t and I give you an epsilon, you can find a delta such that for all t prime satisfying this, then you get this. But then you're saying for all t, I can find an epsilon. And here I'm saying that I can, for all t and for all epsilon, I can find a delta. And that's saying like that for each epsilon and each t, you can give me a delta that works. Whereas here I'm saying for any epsilon, I can find you a delta that works simultaneously for all t and t prime. So it's a stronger statement that happens to be true as well. Right, so this is uniform continuity. And this comes for free when functions are continuous, right? Basically what I'm going to do now is I'm going to show that in a way the convolution of f and g is uniformly continuous with more or less the same delta as g, right? So this delta in principle depends on epsilon. So for each epsilon we have a delta. And we're going to show that, I mean, basically with the same delta or a slight change of delta, you still have uniform continuity, right? So, okay. Let's consider, because we're going to prove that things are continuous, right? Let's consider the difference between f of minus g of t and f minus g, f star g of t. And let me add, let me say here t2 and t1. And I'm going to look at the difference assuming t2 is greater than t1. I have an absolute value here, so that's not really a big deal. I can just flip the roles, right? Okay, why do I care about this? Because I want to write down the two integrals. So I have an integral from 0 to t2 of f of s, g t2 minus s ds, plus minus an integral from 0 to t1 of f of s, g t1 minus s ds, absolute value of everything. Now, I want to compare these two quantities, and it's nice if I can put them both inside the same integral, right? However, the intervals over which you're integrating are not the same. But then this integral here, I'm going to express it as the integral from 0 to t1 plus the integral from t1 to t2, right? We know we can do this for Riemann integrals. If we integrate from here to there, we can stop in the middle and add up the two pieces. Okay, and why do I do this? Well, okay, if I do that, let me do it right here, actually, because I'll need to save up space. This blackboard here is far from ideal in terms of space. Okay, so let me write everything like this. And I'm just going to say, okay, I have an integral. I'm going to write the I'm going to write this guy as a sum of two integrals, but I'm going to write it in sort of the reverse order that I just wrote. There's an integral from t1 to t2 of g t2 minus s f of s ds plus an integral from 0 to t1 of f of s. And now let me do it like this right away. I have another bit of this integral, right? The integral from 0 to t1 of g of t2 minus s, f of s. But I also have this other integral, which is g of t1 minus s, f of s, the thing that I had before here. So if I combine the two integrals into one, I have this. That you can check. I mean, if you go back in the video, you can see that I have exactly this. You just have to use the linearity of the integral here. Okay, now I'm going to say, well, the absolute value of the sums, at most the sum of the absolute values, but I want to do more with that, right? So I want to bound the absolute value of this integral, and I want to say that for this integral is at most the length times the sup of what's inside, and like before we have f g. And now I want to do the same thing here. So I have the length of the interval, right? So I bound the absolute value of this by the length of the interval times the sup of what's inside. Well, I still have the length of the interval. I'm just going to say it's at most 1. But here I have a different term. We are interested in what happens when T2 approaches T1, right? So let me assume that the distance between T2 minus T1 is less than this delta here. Okay, so this is less than delta of epsilon. Here, what do I have? Well, I have the sup of f, which comes from this. What's the sup of this? Well, I'm computing g at a point t2 minus s, computing g at another point t1 minus s, and I don't know much about what s is, right? S varies over this interval. However, I do know that the difference between t2 minus s and t1 minus s is the same as the difference between t2 and t1. Therefore, it's less than delta of epsilon. So this is less than the sup over t minus t prime less than delta of epsilon of g of t prime minus g of t. Now let's go back to our definition of uniform continuity, right? So notice that for any epsilon, so sorry, the choice of epsilon is implicit here. For any epsilon, we have this delta of epsilon, which ensures that when this distance is less than delta of epsilon, this is less than epsilon. Therefore, here I'm taking a sup of things which I know are less than epsilon. Therefore, the sup has to be less than epsilon, right? So there is no mystery here. I'm just saying, okay, these guys are always, right, the difference between g of t and g of t prime for t and t prime this close has to be less or equal to epsilon. So, okay, I can put an epsilon here. So let's look at the end result. The end result is this. That, okay, let me read it just like we had before. It doesn't make too much of a difference. And let me say, this is true if the distance between T1 and T2 is less than or equal to delta of epsilon. Okay, now watch. Now, notice what happens, right? So I said before that T2 was less than T1 just to make this calculation work. But in fact, the formula I get in the end, the bound I get in the end is completely symmetric. So as long as you're willing to kind of flip the rows, they're so similar. Okay, I claim that this proves that f convolution G is continuous, right? How is that? Suppose that now instead of T2, I have a sequence T sub n that converges to, suppose here I have T sub n converging to T1. So I can put T sub n here. Okay, let me erase this because we proved this bound is true, so we don't need it anymore, right? So we use it as a tool, a means to an end. What I have to do is to replace T2 by this T sub n. Here. Okay, so if T sub n converges to T1, this part here goes to 0, right? Again, as usual, this is up lower bounded by 0. And this thing here goes to 0 if Tn goes to T1. What about this other guy? Well, I know that it's less than epsilon when T sub n is minus T1 is less than delta of epsilon. Delta of epsilon is positive, and T sub n is going to T1. Therefore, this thing here is less than delta of epsilon for all large enough n. Therefore, I know, right? So just by, let's use the trick that I used before of taking a limit superior, a lim sup. So I'm just going to say, well, the lim sup of this part is 0. And the lim sup of this guy, well, since I know that for all large enough n, this is true, therefore I have this inequality. And I have it for all large enough n, well, that's what I need, right? So, because now I know that my lim sup is between 0 and this number here, f infinity times epsilon. Epsilon is arbitrarily small. Therefore, I can, for instance, send epsilon to 0. And I guarantee the lim sup is between 0 and 0. Therefore, it's equal to 0. But since this is a non-negative sequence of numbers, it has to converge to 0 if its lim sup is 0. That means that f star g of Tn converges to f star g of T1. Okay? Good. So in the end, what proves that that f star g is continuous is not the continuity of f. All we used here was that g is bounded, that g is continuous and therefore uniformly continuous over 0, 1, and that f is bounded. And that's sort of a hint of smoothing properties of convolutions. Even if f was discontinuous, as long as this integral is well defined and f was bounded, we'd still have exactly the same result. Right? So if f is continuous, if g is continuous, then f star g is continuous. Basically, that's what I'm saying. And also that works also if f is continuous, then the convolution is continuous. Okay, but that's enough of convolutions for now. We now have to quickly go to the other guy. And I just want to, this one I'm going to present as a sketch. Is going to be in a later homework assignment. But I mostly want to explain to you why this is interesting, right? So a typical problem in the theory of ordinary differential equations is to solve a problem like this. I want to find a function f that satisfies f. Let me dry this up a little bit. A typical problem in the theory of ODEs, the Cauchy problem, is that I want to find a function f such that f of 0 is x naught, f prime of t satisfies psi of f of t, for t, say, between 0 and 1. Well, you can ask for a larger time interval, but let's stick with 0, 1 because that's what we're considering. Now, okay, what about this problem? This is a Cauchy problem. This is a very important problem, mathematics. This is the autonomous Cauchy problem because this psi doesn't depend on time. But essentially, all of classical physics consists of problems of this sort, right? All dynamical problems in classical physics can be put in this form if you allow f to be vector value, to take values in Rd instead of R. And in fact, what we're going to do here for R, right, for continuous from 0, 1 to R, could be easily generalized to continuous from 0, 1 to Rd, or continuous any bounded interval to Rd, any compact interval to Rd. Okay, so, right, so how do we, how is this related to that? Well, a function satisfies this if and only if f of t is equal to x0 plus the integral from 0 to t of psi of f of s d sub s. And why is that? Well, if this is true, f of 0, well, the integral is 0, you get x0. And what's the derivative? Well, you differentiate, this disappears, and you just use the fundamental theorem of calculus, right? The derivative of an integral is the value of the integrand at point t. And it's easy, well, it's okay. If this guy solves this problem, if a function satisfies this, it solves this problem. And also immediately, if psi, we're going to assume that psi, I should have mentioned that, is continuous. If psi is continuous, then it's easy to go both ways. You just say, okay, if this is true, then f has to be continuous because it's differentiable. Therefore, psi of f of t is continuous. It can integrate it, and it must be that this thing here holds. So notice, what is this saying? This is for all t in 0, 1, right? So therefore, this happens if and only if the function f is a fixed point of this transformation that I wrote over there. Right? So notice t of f is this function that, well, given f, t of f of t takes this value. So a solution to the Cauchy problem needs to be such that if I apply this operation t to it, I get back the same function. So studying the Cauchy problem for ODEs consists of studying fixed points of such problems. And the nice thing is that continuity of capital T comes into play. And how do you prove it? Let me quickly sketch the proof. Suppose f sub n converges to f. Now I want to look at the difference between tf, say of capital of little t, tf sub n of tf of t. I need to find a bound on this that is independent of t, so that I bound the sup norm, and then I need to find a bound that that goes to 0 with n. Right, so let me just mention that this is a difference between these two expressions. The x naught disappears, right? So I'm going to be left with, well, this is exactly equal. A t times psi f of s minus psi fn of s psi f of s, right? It's a difference of two integrals, so it's the integral of the difference. Now I use the bound that you should be getting used to by now. Okay, this is not A, right? This is 0. That's just the length of the interval. Just get bound by t times the, this is a composition, right? Psi of f sub n minus psi composed with f. So we have our bound. So t of fn minus t of f is less than the difference between the two compositions. Now watch. Now the thing to be done is to prove that this thing goes to 0 if f sub n converges to f. Let me remind you, this is the soup norm. Okay, and how do we prove that? That is a little bit tricky because we need the supremum, right? So I'm going to show it to you, but just... So remember that we proved that any convergence sequence in a Banach space is bounded, meaning that sup of n in Fn, infinity is less than m, and the same, well, you can choose m, so that's also true. What does that say? It means this. So if I look at the graphs, 0, 1, of all functions f sub n and f, their graphs are all contained in this strip. Right? So maybe one function is like this, the other is like this, the other is like this, but all the graphs are contained in this strip. Right? Because the sup is just the maximum value. What you have to use, remember, you want to prove that this thing here, psi of f sub n minus psi of f goes to 0. And the exercise that you need to do is this. You need to use the fact that psi over this contact interval is uniformly continuous. Now, if you just use continuity, it's easy to prove pointwise convergence, that psi composed with fn computed f sub n computed at t converges to psi of f t for all t. But that's not enough. You need uniform convergence. And for that, I claim you need to use uniform continuity of psi. So as I said, this is going to be an exercise. It's an important exercise, a prelude to things that are going to come. So please do it. But for now, that's it. Thank you very much.